Advanced Ceramic Nanocomposites Lecture 4 Ceramic Nanocomposites in Industries. High-performance materials, so-called nanocomposites, have unique features. Engineered plastics and elastomers are where nanocomposites are most in demand, with an anticipated 25% annual growth rate. Their potential is so great that they are useful for many applications, from packaging to biomedical ones. The many forms of matrix nanocomposites are covered in this year, um, with an emphasis on the need for these materials, their methods of manufacturing, and some recent findings regarding their structure, characteristic, and possible uses. The necessity for such materials in the future, as well as other intriguing application, are projected. Application of nanocomposites offer new technical and commercial potential for numerous sectors of the aerospace, automotive, electronics, and biotechnology industries because to their environmental friendliness. Uh, when at least one of the face of the composite exhibits dimensions in the nanometer range, the composite is called nanocomposite. Also, the term nanotechnology is new functional objects and structures with nanoscale metals or ceramics in the 4th century. Uh, uh, object with dimension of nanometer already exists. For example, Roman glassmakers were creating glasses with nanoscale metals in the 4th century. Nanocomposite materials have emerged as suitable replacement for the absurd limitation of microcomposites. They have been shown to the 21st century resources in terms of design rarity and property groups that are not present in typical composites. They do, however, provide preparation difficulties related to the control of fundamental structure and stoichiometry in the nanocluster phase. High-performance materials called nanocomposite exhibit unusual property arrangements. Their potential is so obvious that they are useful in a variety of applications, from packaging to biomedical ones. This uh, lecture highlights the necessity of these materials for presenting several matrix nanocomposites, their techniques of processing, composition, characteristics, and possible applications will be discussed in this lecture. Due to their small size, high surface area, and phase relationship at the interface, nanocomposites imply unique features. They stand out for their potential to create high value added materials such as catalysts, biomaterials, and pharmaceuticals that work well. When the particle size falls below a specific threshold referred to the critical size. It has been claimed that changes in particle attributes can be seen. Interaction at phases interface typically improve when diameters approach the nanometer range. Additionally, the discovery of carbon nanotubes and their subsequent applications to create composites that displayed some of the special mechanical, thermal, and electrical properties connected to carbon nanotubes provided a fresh and exciting dimension of this field. In addition to being ecologically beneficial, nanocomposites currently presents new technological and commercial potential for all sectors of industry. The conventional powder method as a polymeric precursor route, spray pyrolysis, vapor techniques, and chemical methods such as Sol-Gale process, colloidal and precipitation procedures, and template synthesis are the most widely used technology to creation of carbon multi-wall nanocomposites. Ceramics are frequently vertical and prone to fracture as a result of crack growth. By adding a ductile metal phase or another ceramic to the matrix, ceramics can be made appropriate for engineered purposes. Because of interaction between the various phases, the matrix and the reinforcement at the phase boundaries, mechanical properties including hardness and fracture toughness are improved. Major breakthroughs have accompanied the discovery of novel alloys. The discovery that intimately combining copper and tin produced a metal that was significantly stronger than copper led to the invention of bronze. The majority of metal nanocomposites based on nanocrystals show the remarkable resistance to grain development regardless the synthesis process. In addition to the microstructural and compositional characteristic, porosity, impurities, grain size, distribution, texture, and microstrain resulting from the process of nanocrystalline materials are also related to the thermal stability and the mechanism involved in nanocrystalline materials. Two different metal nanocomposites can be simplified mixed together to produce new qualities. Numerous studies have been conducted on nanocomposite systems like carbon nanotubes. The quantity of publication on the topic has consequently increased, occasionally even including evaluation. A review on powder metal nanocomposites cover processing issues such as these involving layers, silicates, conducting and biodegradable polymers-based system, fiber reinforcement and structure, morphology and property aspects, as well as application and perspectives such as important opportunities and difficulties in creation of structural and functional fiber nanocomposites. Spray pyrolysis, liquid metal infiltration, rapid solidification, vapor techniques, electrodeposition, and chemical procedures, including colloidal and Sol-Gale process, are the method utilized to process metal matrix nanocomposites. The fabrication of ferrum-based nanocomposites involves solidification methods. The phase devitrified nanocomposite steel is stressed by Brenagam. The high nucleation frequency inside the constrained window for the grain development prior to impingement was responsible for the production of nanophase. The wettability between the matrix and particles was made better by use the ultrasound. Here you can see some parts from nanocomposite metal matrix composites, which could be enhanced by particles and elongated nanostructures. For example, we will discuss the research and development process from idea to the product. We will illustrate some steps. The first one, how to what we can improve, how we select the materials, the technology, and what we want to achieve from nanocomposites. The next one, we select the suitable methods and processes, how to design which help us to design the microstructure of materials. And finally, we will discuss the effect which can be achieved from the implementation of the materials technologies. It could be the lower price, better, good quality product, energy efficiency, ecologically friendly process, and other. For example, we observe the effect of self-healing for ceramic nanocomposites. This effect could be used to produce ball bearing with self-healing effect based on ceramic nanocomposites. Self-healing is a certain type of unique physico-chemical property by which the material can be able to repair automatically the damage or fracture part of the tissue due of the part, for example, tissue due to the accident and used successfully at the time of operations. This damage may be due to accident or by aging processes. The self-healing composite acts as a significant healing agent to create an external trigger by initiating the process. Self-healing material is a novel, sustainable material and can be successfully applied for many fields of industry. In the currently known self-healing ceramics, micro-crack healing is achieved by oxidation reaction at high temperature and therefore requires at least the combined presence of material which can be oxidized, so-called sacrificial particle, oxygen, and high enough temperature. Based on this approach, both intrinsic and extrinsic self-healing at high temperature ceramics have been developed. In the process of extrinsic self-healing for ceramic oxides, discrete healing particles such as granular particles, fibers, or whiskers are introduced into the inert ceramic matrix prior to the synthesis. These particles essentially remain inactive through the material usage until they encounter a nearby crack. At this point, a localized chemical reaction, typically oxidative, is initiated at the interface between the crack and healing particle. This reaction generates reaction products that expands potentially facilitated self-healing behavior by restoring mechanical strength. Crucially, for effective self-healing, this reaction product must also form strong bonds with the surrounding cracked mix matrix material. And here you can see the schematic how this process take place. We form the composite materials with sacrificial particles embedded in matrix. During the exploitation, this material at high temperature and correct formation, the oxygen uh, trapped to the crack and the sacrificial particles oxidize. The oxides fill the gap and heal the crack. But the main idea that properties of initial material and healed material have to be the same. In order to fill a crack gap with a healing agent, it is required that an adequate volume expansion occurs upon oxidation of the healing particles, such that the oxide format can fill a new free volume within the material created by the crack. This volume expansion can be estimated by considering the oxidation reaction. To ensure that fractured surfaces are completely bridged with the healing oxide, a limit of more than 50% is set as a minimal requires increase in specific volume. Based on a simple model of crack gap filling presented Bohemia in the dissertation, uh, the volume fraction of healing particles with size between 1 to 10 microns necessary to fill a crack about 1 micron in width is less than 30%. All healing materials passing the previous selection steps exhibit a possible volume expansion upon oxidation. And here you can see which ceramic and metallic materials could be selected for the composites as sacrificial material. In our work, we select the zirconium nitride as a healing agent, and we synthesize the silicon nitride based composite nanopowders. As I say, a selected healing agent and composition we start to prepare it. The combined synthesis of silicon nitride with zirconium nitride ultra dispersed composite powder from a mixture of laboratory synthesized silicon nitride powder and commercial micron-sized zirconium powder without subsequent milling was developed in our work. Thermal synthesis was carried. Thermal synthesis of mixture silicon nitride with zirconium was carried out in two stages in vacuum, the first stage, and gaseous nitrogen in a single technological cycle. In the first stage, the solid-state interaction in vacuum take place between silicon nitride and zirconium. Reaction mixture occurred, but reaction diffusion mechanism on boundaries of zirconium and silicon nitride particles. And as a result of dissociation of silicon nitrates take place was accompanied by formation of a highly active precursor. The diffusion of nitrogen into zirconium occurred with the formation of zirconium nitrides, and diffusion of silicon occurred with the formation of lower silicate of zirconium. And finally, the combination in single cycle of the developed process of first step vacuum heat treatment at lower temperature and nitriding at high temperature up to 1200 centigrades of the precursors, developed precursors. We obtain the nanoceramic composites, ultra disperse composites with particle size below 200 nanometers. This composition was mixture of ultrafine particles, silicon nitride, and nanoparticles, zirconium nitride. It could be synthesized in a wide concentration range, but we work with composition in 22 volumetric percent of zirconium nitride as a healing agent. As previously observed in my lectures, we developed the special non-linear spark plasma sintering schedules to densify different nanopowders of high melting point compounds and mixtures to forms the nanostructure in materials and densify these materials to a near fully dense to a near theoretical density. Previously, we work with commercial nanopowders. These powders have a quite high price, but now we develop the original technique how to produce without mixing nanopowders, directly produce the composition of, for example, silicon nitride with zirconium nitride, and it's a good way to consolidate this composition. We develop the special non-linear spark plasma sintering schedule for developed nanocomposition of self-healing composites will be produced. In the manufacture of complex shape products by the spark plasma sintering method from composite powders, silicon nitride with 22 volumetric percent zirconium nitrides, which components conduct differently electric current. It is important to choose a condition regime that provides a homogeneity of the structure of the material. To determine the characteristic features of consolidation and synthesis composite powders, spark plasma was performed in the following regimes. The pressure was around 40 megapascals, heating rate 70 centigrades per minute, and we sinter it up to temperature 1700 centigrade with some isothermal cold. But moreover, we developed the special non-linear regime when the densification rate stays stable up to the temperature uh, 1650 centigrade. Despite the fairly good sinterability of the composite powders containing a high volumetric of zirconium nitride, we tested on the 33 volumetric percent of zirconium nitride and find that these materials consolidate quite good because it's a lot of conductive phase, but zirconium nitride with high volumetric percent during oxidation tests damaged and not work properly as a healing agent. It means that we have to work with a lower volumetric percentage of healing agent. In this case, it's zirconium nitride. To promote a densification process of silicon nitride with zirconium nitride composite, where zirconium nitride is below 30 volumetric percent in composites and obtain almost fully dense ceramic, we additionally added the yttrium oxide and aluminum oxide powders, and as synthesized silicon nitride with 22 volumetric percent zirconium nitride powder was mixed with yttrium oxide and aluminum oxide powders. As a result of mix, we obtain the homogeneous mixture and consolidate it using spark plasma sintering. We obtain the balls blanks and apply the non-linear spark plasma sintering regime, which consists of a few stages. Where the pressure and heating rate changed depending on the densification rate of the material. On the first stage of spark plasma sintering schedule is performed at high heating rate until the relative rate of the material at shrinkage attains 70%. The intermediate, this one is quite high heating rate. The next step is intermediate stage in which characterized by decreasing in the heating rate and increasing of pressure. The final stage when the relative density achieve 80 to 90% is characterized by minimum admissible heating rate. At the beginning of spark plasma sintering, a relatively low pressure applied, which is sufficient to provide a good electric contact between particles and between punches and materials, matrix and materials. In the process of spark plasma sintering consolidation, pressure constantly smoothly increased in this non-linear regime and is controlled at the points of switching over the heating rate, which makes it possible to maintain a high densification rate and achieve a high density of sintered material, as you can see. The nonlinear spark plasma sintering schedule for silicon nitride with zirconium nitride composite implies a change in the heating rate after attaining 800 centigrade and 1200 centigrade. Moreover, in the indicated temperatures range, the working pressure gradually changed from 6 kilonewton to 16 kilonewton and remains constant in holding up to 1650 centigrade. This regime make it possible to prevent fracture of graphite dies and obtain dense ball lengths and predetermined size. Consolidation was performed in a graphite die, and here you can see the temperature dependence of relative density and shrinkage rate of ball and cylinder blanks from the composite powder with a mass of around 9 grams during spark plasma sintering. According to the obtained experimental data, the densification of silicon nitride, zirconium nitride composite material begins at around 1000 centigrade, but densification proceeds at different rates up to the temperature 1650 centigrade. A maximum densification rate 3.5 millimeter per minute is achieved at the temperature around 1300 centigrade for bowl-shaped specimen. For the cylindrical specimen, we observe two peaks at temperature around 1400 centigrade and 1600 centigrade, at which a maximal densification rate is around 2 millimeter per minute is achieved. The difference in densification rate is explained by the difference in the shape of sintered products. It's quite important for spark plasma sintering techniques, because if we try to obtain materials with different shapes, we have to determine the special regimes, special schedules of SPS for these materials. For example, for the ball-shaped specimens, the densification rate is determined by color 2 millimeter thick, which forms around the ball. This region contacts with the die and is overheated, whereas the temperature is measured near the upper point of the ball is different from the region of color. The first maximum of the densification rate corresponds to sintering stimulated by zirconium nitride particles, and the second maximum is due to the formation of the liquid phase based of yttrium and aluminum oxides. A short isothermal holding around 1 minute at high temperature makes it possible to obtain an optimal homogeneity of structure and the highest relative density, around 97%. The microstructural analysis shows that in both cases, balls and cylinder fine-grained structure were obtained. Zirconium nitride and silicon nitride grains are homogeneously distributed over the whole volume of specimen, and grain size of silicon nitride is around 200 nanometers, and the grain size of zirconium nitride is like the same. In the established optimal spark plasma sintering regions, a small batch of ball blanks with diameter around 16 millimeters was manufactured from silicon nitride, zirconium nitride composition. The ceramic balls were polished to the diameter around 13 millimeters. We measure previously the Vickers hardness at around 22 GPa and fracture toughness using method of induction. It was around 6 MPa per meter. The realization of a mechanism of self-healing for these materials, self-healing of surface defects in friction, is possible in two ways. In the first case, self-healing of defect occurs when wear products penetrate into it, and in the second case, self-healing effect is induced by oxidation of the healing agent, its zirconium nitride, on the surface of a defect when it is located in a tribocontact region or when a tribocouple is operated at elevated temperatures. For the complete evaluation of process of self-healing of defects in silicon nitride, zirconium nitride ceramic, it is necessary to determine a maximum size of defect that can be healed and the generalized temperature at which a self-healing process will be most efficient. It is expected that a product healed by zirconium oxide and the initial silicon nitride zirconium nitride composite have similar properties. In order to that the crack filled with the healing agent, the volume expansion that occurs as a result of oxidation of zirconium nitride must provide filling of a new free volume created by a crack in the material. Under standard conditions, the components of ceramic bearing based on silicon nitride zirconium nitride composite can successfully operate up to 600 centigrade, as we estimate. Above 650 centigrade, the process of intensive oxidation of zirconium nitride take place. And the structure of materials could be destroyed. At the same time, the moderate temperature and effect of self-healing of defect in the zirconium nitride containing composites is observed and studied in our investigation. Among defects that are successfully self-healed and cracked cavities that size is around 50 up to 100 microns could be successfully healed as we showed. And properties of this material is the same. It means that we test the bending stress and of healed ceramics and bending stress of initial material, sintered material. It is the same measurements showed. This material, as we show you, could be successfully utilized for a hybrid or ceramic ball bearing or other bearing, and it could be used at elevated temperature and for a long time, because the healing effect take place. We show how to produce, how to obtain product from idea. Idea is it was a self-healing development of self-healing materials to the product. Product is a ball bearing uh, hybrid ball bearing. And finally, I want to say that in this lecture I demonstrate some examples how you could provide your research and development work from idea to a real product. It should include additional aspects like market analysis, seeking of conversation with the potential end users, but these aspects will be reported in other lecture courses. Thank you for your attention.